Okay, this video is going to cover two sections that we skipped earlier on in the semester. Section 5.5, which is the law of sines, and then section 5.6 will be the law of cosines. Okay, so basically what these laws are for and what these two sections are going to be about is solving triangles. So the goal is to solve, and what does that mean? To solve any kind of triangle. And to solve a triangle means to find all of its angles. So let's say in other words, i.e., so in other words, to find all three angles, right, because there are three angles in a triangle, all three angles and all three sides. The measure of all three angles and the measure of all the three sides. Okay. So the way the textbook puts it, and the way that I was taught it actually as well, is, there's like different sorts of problems you can get, like a side angle side, or a angle side angle, or a side side angle, all these different categories of things that you're given, and then based off of those what kind of info you're given, there is like some algorithm or process you should use for solving the rest of the triangle. I don't really like that way of teaching it or thinking about it. I like to just say use the law of sines if possible, because the law of sines is very easy, at least relative to the law of cosines, which we'll see in a moment, that the law of cosines is a bit more involved as far as the calculation goes. It's basically like a beefed up Pythagorean theorem. So essentially what I'm going to tell you is use the law of sines whenever possible, and if it's not possible, if you end up in one of the cases where it's not possible, then use the law of cosines until, usually you'll just have to use it once, and then you can just fall back on the law of sines or other techniques if they apply. Okay, so first of all, let's talk about what the law of sines actually says. So let me give you a picture here for just some generic triangle. I'm going to denote its angles by capital letters. So this is angle A, this is angle B, and this is angle C. And I'm going to denote the sides with lowercase letters, and the orientation is going to matter here. I'm going to say that the side opposite of capital angle A, I'm going to let that be lowercase a. That's the side. So it's the orientation matters here. I want the letters to be opposite of one another, just for the sake of the formula I'm about to write down. Opposite to angle B, I'm going to have side B, and then opposite to angle C, I'll have side C. So using lowercase letters for the C. And what the law of sines tells us is it gives us a ratio to compare the sine of the angle versus the side length opposite to that angle, and it gives us a ratio that says the sine of angle A over, or a proportion, I guess it's a proportional relationship, over the side length A is equal to the sine of B, sine of this angle B, divided by side length, lowercase b, and is equal to sine of capital C over lowercase c. So this is really more than just one formula, right? There is this formula. It says that the relationship between angle A, angle B, side A, and side B. There is this relationship between B and C, and then of course this relationship between A and C. right? So it's 3 formulas in one when I write it all. And this is the typical way that the law of sines is written. It's all nice and neat and compact into one string of equalities there. Okay, so as far as a proof of this goes, I'm not going to ask you to know the proof or anything, but just because it's quick and it uses a fact that you may not know, there is a generic area formula for a triangle. You probably are thinking 1/2 base times height, but there's a more generic one, because what's the problem with the 1/2 base times height formula? You may not know the height, right? You may only have 2 sides of the triangle and it may not be a right triangle, and you may have trouble figuring out what the height of the triangle is. And the area formula is A is equal to 1/2. Okay, now do I want to use the same letters here because I need to be careful? Yeah. A times B, so this is sort of looking familiar if A and B were base and height, but then I'm going to tack on times sine of the angle between A and B, which in our current orientation here, as I've labeled everything here, it's sine of C. So in general, the area formula for a triangle, you just take the product of 2 of its sides times the sine of the angle between the sides, and then times 1/2, and you get the area of a triangle. Okay, so we never talked about this, but it's kind of a useful thing for just knowing a generic area formula if you don't know the height of a triangle. So why am I bringing that up? Well, I can get 3 different representations of the same area for this particular triangle, the way I've notated these sides and angles. I can get A is equal to 1/2 AB sine of, so the point is, the 2 sides that you pick, the sine of the angle needs to be between those 2 sides. So here's sine of C. And by the way, the area is also equal to, I could pick like 2 other sides, like B and C, 1/2 BC, and then I would have sine of A, right? This A, let me hang on one moment. This A is area. Let me make it a script A, like fancy, make it look fancy, so I know that's area, and this is the angle A. Not the same, okay. And what is the other orientation I could use for finding the area? I could use A and C, because the point is, with this area formula, you can pick any 2 sides as long as you know the angle between them. Okay. These are all equal because they all represent the area of this triangle. They're just different ways to write it down. Now, I can divide all of the 1/2s off. What am I doing right now? I'm deriving the law of sines formula because it's very nice and clean. A very nice clean derivation that also shows you this generic area formula. And now what should I do? I'm going to divide everything by ABC. You'll see that'll make everything clean up very nicely. So I'm going to divide by ABC. That'll make a lot of stuff cancel out. In fact, it'll make everything that I want cancel out. So A and B cancels here, and I end up with sine of C over C. That's a little c, and this is a capital C, right? That's the angle, and that's the side length. And then here, B and C cancel out, so I have sine of angle A over side length A. So you see, there it is. Very nice, very clean derivation of this law of sines. Just using a little geometry fact here and a little bit of algebra. Okay, let's practice using the law of sines now. For this first example, pretty much actually for all of the examples, we're going to be solving triangles. Solve the triangle. Remember, that means find all of its sides and all of its angles. So let me draw the triangle here. Let's see. And that. Okay. And in the picture, they went ahead and labeled this as B, this is C, and this is A, so that this is little a, this is little b, and this is little c over here, and we're given that little c is equal to 80.4, so we're given that side measure, not given a or b, and we're given that this is 20 degrees and this is 25 degrees. So we need angle B. We need angle B. Well, really we should say measure of angle B, but that's not what our text does. So, anyways, okay. Now, angle B, we do not need any kind of fancy law for. This is just geometry, right? The sum of the three angles in a triangle is equal to 180. So angle B will be equal to 180 degrees minus these smaller angles here, which is 135 degrees. Okay, that just came from geometry. The other two things we need to know are A and B. We can use the law of sines for this. So, which of these relationships should we use? Well, for instance, we would not want to use this one, sine A. Can we see that? We would not want to use this, sine A over A equals sine B over B. Why? Because we don't know A or B, right? So we don't want to use both, we don't want to have two unknowns in our equation. So we better use some other combination, right? Some other combination of these equations, maybe this one. Because I know little c, and I know all of the angles, right? I know all of the angles, and the only unknown in this case would be b, the little b, so I can use this to find little b. So I'll say sine of b over little b equals sine of capital C over little c. So I'm going to say sine of 135 degrees is equal to sine of 25 degrees, because that's angle C there. Oops, I'm leaving out the fraction part. Over B, this is over B, and this is over 80.4. Now I need to do some algebra to solve for b. To solve for b, since b is in the denominator, I need to go ahead and multiply b over here. So I'll work this out. For this example, I'll work out the algebra explicitly, but then I'll probably start skipping steps. In the later examples. Okay, now I'm going to divide by this whole thing, right? Because it's attached. I had to get b out of the denominator, so I multiplied by b on both sides, effectively canceling out on it out on this side and sticking it over here. Now I need to divide by this whole thing, but when you divide by a fraction, that just flips it upside down. So I'll still have sine of 135 here. B will be isolated by itself, and I'll multiply over here by this fraction upside down. 80.4 sine of 25 degrees. And this is what needs to get popped into the calculator. Sine of 135 is actually a nice angle, but I'll just pretend like I didn't know that and say 80.4 times, am I in degree mode? Yes. Times sine of 135 divided by, that was 25 is not a nice angle, so okay. And I'm getting that, I'll flip it around, b is equal to 134. We should, we'll say approximately, how many digits? Yeah, I guess we'll go to the 10th place. 134.5. Cool, there's b. We're not done though, right? Because we need angle b, which we found via just normal triangle geometry, or normal, I mean like easy triangle geometry, right? We found side B via the law of sines, and we'll use the law of sines again to find side A. And now for side A, I could use any relationship now because I have everything. Out of these 6 things, I have all of them except for side A. So I could use this relationship, or I could use this relationship relating A and C, right? As long as A gets involved, because that's what I want to solve for, right? So I have options now that I'll just do. I'll just set A equal to C. I think it's kind of better form to use the thing that you were originally given instead of the thing that you found and rounded. It's just kind of better form. Instead of using B, instead of saying sine A over little a equals sine B over little b, I'll use C again. Sometimes you have to use what you what you calculated in a previous step, though. Okay, so sine of 20 degrees is equal to sine of 25 degrees. Oops, I neglected to write down the fraction part. There we go. Okay, now in a similar way, I'll multiply by A and then divide by this whole thing. So you should pause and see if you can get what A is equal to. And you should get A is equal to sine of 20 degrees times this fraction upside down. So 80.4 over sine of 25 degrees. Okay. Okay. And I'm getting approximately, A is equal to approximately 65.1. And now we have all 6 things. All 6 things here. So what the book calls this, and what this would be called if you wanted to like look it up on YouTube or something, is side angle angle. That's what they call it. Side angle angle. So this is how you'll see it. Side angle angle case. Okay. So there are other cases, right? There's, well, a lot of other cases, for different kinds of things you can be given. So let's see here. Let's try a different orientation or different given set of data here. Let's see, let's solve this triangle. Let's say, okay, so the instructions are still solve the triangle. And we have something like this. Okay. Angle A is 80 degrees. We don't know angle B and we don't know angle C. So this time we don't know 2 of the angles, but we have 2 of the sides. This would be the so-called, what are they called? Side-side angle case, where you're given 2 sides and then an angle that's opposite to one of the sides. So in this case, we're given this side is opposite to this angle, so we consider it side-side angle. As opposed to the other case where you're given 2 sides and an angle, which deserves its own little case, and we call it, so if you're given an angle between the 2 sides, we would call it side angle side, SAS. I'll work one of those too. That's let's see here. Okay. So you'll see none of these really go that differently, even the one I'll work in a moment with the side angle side. There is something to say about special cases of this so-called side-side angle case. You can get into some weirdness where there is no such triangle that can satisfy the given info. or you can get into a case where there are two such triangles that do satisfy the given info. So we'll look at those. But first, this is like the first normal case where there's nothing fishy going on with it having no solution or anything like that. So we have, maybe we should write down what we have and what we might want. So we have, or we could say given, capital A, angle A, right? What is this side? They didn't label it for us as far as letters go, but this would be lowercase b, right? And we have lowercase a, because remember that the letters, you got to be able to get your naming convention right, because that law of signs depends on how you name these things. And remember that it's always named across. The side is, the same letter is used for the side across from the corresponding angle. Okay, so we're given this. We need capital B, capital C, and lowercase c. Okay, so your strategy here should be to just pick one thing and go for that and make it the only unknown in your equation. So if I'm going for angle B, I definitely know I'm going to have this side of the equation. Now, what would I want to choose so that my only unknown is this capital B? Well, I definitely would not want to pick sine of C over little c, right? Because I don't have either of those, so that would be an awful choice. I want to pick sine of A over little a because I have both of those in pieces. Okay, so I'll say sine of B, which is what I'm looking for, over little b, which is 3.4, is equal to sine of A, which is 80 degrees, over little a, which is 6.5. I want to isolate b, so I'll multiply by 3.4 on both sides. It's multiplied by 3.4. And then I'll take the sine inverse on both sides. Sine inverse of sine of 80 degrees times 3.4, and then I'll divide by 6.5. Okay, and I'm getting 31 degrees, so B is equal to 31.0 degrees. They only give me a whole number for the given angle, so I'll just round to a whole number here. 31 degrees there. Alright, now I will go to C. To find C, I could use the law of sines again, but I really don't need to because I have two of the angles now, right? So I know this angle C is going to be equal to 180 degrees minus angle A, which is 80 and then degrees, and then minus angle B, which is 31 degrees. So that's going to equal 69 degrees. Right, 130, yeah, okay, 69 degrees. Okay, so that's done, that's done. Now I just need little c. So I'll say, you have options now. I'm going to say sine A over little a is equal to sine c over little c. I'm solving for little c. By the way, you could solve for little c before you plug stuff in here. I could go ahead and say little c is going to be equal to, do a little bit of algebra here, it should be sine of c and then times, so multiply this over and then divide this whole thing over a all over sine of capital A, if you like to do it that way. Okay, and now I'll go ahead and plug in. Sine of 69 degrees, right, wait, yes, times A, which was 6.5, over sine of 80 degrees because that's what A measured as. And that's going to give me times 6, okay, divided by sine of 80 degrees. 6.16. They were rounding to the 10th place, so I'll round to the 10th place as well, so I'll say 6.2. So now I've got C solved for as well, little c. So there it all is. So this is, B is 31 degrees, C was 69 degrees, and little c here was 6.2. All right, let's do an angle. What was I going to do? Side, angle, side. Side, angle, side. Okay, so we are trying a side, angle, side. So, again, same instructions, and this is going to be a side, angle, side, meaning we're given the angle between the two sides. So let's just kind of see how this goes. We're given this triangle with a side length here of 340 and a side length here of 290 and an angle between of 60 degrees. Okay, so I said earlier that all of these will go the same, but do they? I didn't really mean that. I didn't really totally mean that. Because this particular case, well, let's just see what happens. Let's first of all, let's label A, B, and C. So we weren't given like a labeling convention in the problem, so we need to pick how to label these things. So I won't think about it too hard. Just call that A, B, C, so that this side here is little a, this side across from angle B is little b, and then this side here is C. Okay, so now I'm going to go ahead and, just to keep things straight, I'm going to write down what I'm given, which is a, little b, and capital C, and what I need, which is little c, and then the two angles A and B. Okay, so I'm just going to go straight for little c, so I know I need to get this involved if I'm going for little c. That's fine because I know angle C. Now what I want to pick on the other side needs to have no unknown values in it, because I already introduced an unknown, the one I'm going for, which is little c. But notice that this won't work. Why? Because I don't know capital A. But also, if I try sine of C equals, if I try the other sort of form of this law of sines, whoops, sine of B. Typically we write law of sines without the like parentheses. It's just kind of like just notation without the parentheses around the input for whatever reason. So I'm sticking to that. This won't work either. Why? Because we don't know capital B either. Okay, so we can't find C, but does that mean all hope is lost? Well, pretty much yes, but let's just let me prove it to you that we really do need another tool to be able to solve this triangle. Let's see if we can get A. So sine of capital A over little a, that's no problem so far because I know little a. So now on the other side I want to introduce no missing values, no other missing values, because I've already introduced my missing value that I want to solve for, which is the capital A. That's what I'm going for. But in any case, I'm going to end up with another missing value here. You see why? I can pick sine of B over little b, but don't know B. I could try sine of A over A equals sine of C. Whoops, I did it. Oh well. But I don't know, so that's capital C in there. but I don't know little c. That's little c. Okay, so in either of these cases, it won't work to find A, and a similar thing is going to happen for B. So I can't find any of these for side angle side when the angle given between when the angle given is between the two sides. We're going to need another technique, and that's where the law of cosines is going to come in. So let's stick a pin in this problem. Let's talk about the last case that we can solve strictly with law of sines, and then we'll get the new tool under our belt, and then we'll come back to this kind of problem. That aside. Okay. Example 4. So there is the problem in the side-side angle case, which we've already done one. This one, side-side angle, where you can possibly have 1, 2, or no solutions. So the case of side-side angle can possibly have 0, 1, or 2 solutions. Is that what I think I said that incorrectly a second ago when I was looking around for the paper, but it's 0, 1, or 2 solutions. You can have 0 solutions if it's not possible to build a triangle out of the given data. You can have 1 solution, which is like just the nice normal version that you don't even know anything's wrong, like in example 2. Or you can have 2 solutions if the data can actually build 2 different triangles, just based off of the way it's oriented, or the length of the sides and the sides of the angle. So let's look at the, what should we do first? We'll do the 2 solution case. So let's see. Okay. Where's the triangle? Here it is. So we have A, B, so A is here, maybe B is here. Am I drawing this sort of? Well, let's make angle A here, angle B here, and angle C here. This angle is given as 43.1 degrees. Side A, little a, is given as 186.2, and side B is given as 248.6. So this is a side-side angle case. Okay. Let's go ahead and find angle B. So I'm going to skip the little step where I write what we're given and what we need, and I'm going to go straight for angle B. Sine of B over little b, and I definitely want to use A here because A is the angle that I know. Sine of B, so that means, say, do some algebra here. You can pause and solve for angle B. I'm going to go ahead and do it all at once here. Sine inverse, I'll multiply by B, right, and then take sine inverse, so it'll be B times sine of A over little a. This is, yeah, that's fine. Can put it all over one fraction there. Okay, so that means B is going to be equal to sine inverse of 248.6 times sine of 43.1 degrees over 186.2. Calculator went somewhere. Okay, so I'm getting B is approximately 65.8 degrees, but this is where we should stop and say, wait, doesn't sine inverse not as a function, but as an operation, give two answers? And it does. It does, if you recall how that sine inverse operation is working, it does yield two answers, possible angles between 0 and 180. In fact, the only time it yields one answer is if it's exactly 90 degrees, right? When sine is equal to, when the input is just 1. Or the input of into the inverse function. Anyways, so it can give two answers either in the first or second quadrant, right? What is the other angle then? How do we find that other angle? This angle's in the first quadrant. That's what the calculator's going to give me. How do I find the other angle? Well, I'll just take this angle away from 180 because it's supposed to be in the second quadrant, right? So that geometry tells me if my angle is here, I'm just going to kind of put it here, like that's 65.8 degrees. And there's another angle that's like symmetric to it over here. And I want to know what is that angle, what is the bigger angle, whoops, from here to here. Well, I'll just take 180 and subtract the 65.8. So I'm getting 114.2 degrees. Now, this happened in example 2 as well, but I didn't mention it, and I'm about to show you why here. In this problem, are both of these legitimate angles? So to answer that, I'm going to split into two cases, into two separate triangles, and see if both of these angles yield angle C's that make sense. So let me show you what I mean by that here. So let me call B1, let's just go ahead and set B1 equal to 65.8 degrees and B2 equal to 114.2 degrees. Okay. And let's consider the case of B1. If B1 is equal to 65.8 degrees, then what is C1? Let's go ahead and label all of the things in this case with the subscript 1, because we have two different possible triangles now. So what is C1? Well, C1 will be equal to 180 degrees minus A1, which is, well, A is 43.1 degrees, so 43.1 degrees minus 65.8 degrees. Okay? 180 minus 43.1 minus 65.8 is 71. Okay, so that is a legitimate angle. That means this does represent a possible triangle, and we have to go find the sides to it now. Or rather, that missing side of the lowercase c. What about the B2 case? If B2 is equal to 114.2 degrees, then what? I should have a comma there. Then what is C2? Well, C2 should be equal to 180 degrees minus the angle A, which is the same, and then minus this. Now, is this going to be a problem? Let's see. 180, like is that 114 angle too big? Minus 114.2. Ah, it's not. C2 is equal to 22.7 degrees. So, both of these represent legitimate angles that could be given for angle C. What about that example 2, where we had the same kind of situation, a side-side angle like this, right? And I just completely ignored splitting it into cases. Well, I was kind of, brushing some things under the table, but what happened here? What is the other angle that possibly could have been given from this sine inverse operation here? Well, I would take 180 minus the given angle, 31, to get 149. So if there was another angle, it would be 149. So when I went to solve for angle C, so if like B2, right? If B2 is equal to 149 degrees, which I would find that from this, the sine inverse thing outputs two solutions. One of them, the calculator always gives me. It's going to give me the one in quadrant 1. The one in quadrant 2, I have to find manually by taking this operation. There it is. 180 minus that angle in quadrant 1. And then I go check it. If B2 is equal to 149, then C2 is, what is C2? C2 is going to be equal to 180 minus 80, because that's angle A that was given, right? Minus 80 minus 149. You see why that's going to be an issue there? 180 minus 80 minus 149 is negative 49 degrees. That's not possible. So there is only one solution to this. Really what you should do each time is you should do this and confirm that you've either got, one or two solutions, or possibly no solutions too, right? We'll talk about that case too. Okay. So basically what's happening, like in this case, is the second angle that's in quadrant 2 that this sine inverse operation outputted, it's just too big. It's just too big, right? It's a big angle. There's already a big angle. So there's just not room for C. Over here, though, in example 4, we have a big angle from quadrant 2. It's not quite as big, right? And angle A, the original given angle, is not quite that big either. So there's enough wiggle room for two angle C's to exist, namely these two. Okay, so we still need to find side C, and that's going to be two different C's. Okay. So for C1, little c1, we'll use capital C1. So I'll say sine of C1 over little c1 is equal to sine of, what side there? I could use, it doesn't really, yeah, let's say, it doesn't matter. Sine of b1 over little b1, which all of the stuff that's given is not going to change. Like angle A, side B, side A, this is not going to change. The only things that are changing are that the angle B, the angle C, and then the side C. Okay. So little c1 here is, now after I get all this stuff written down, I'm going to organize it all for you. I'll redraw the picture. Let's see, multiply, so sine of c1 and then times b1 over sine of b1, and then plugging all this stuff in, so c1 being 71.1 degrees, b1 being 65.8, and the side measure b1 being 248.6, we're going to get c1 is approximately 257.8. 257.8. Okay. And now let's find C2. I'm running out of room. I want to keep this sort of on the same page. I can kind of do like that. So yeah, that's fine. So I have B2 there. So now sine of C2 over little c2 is equal to sine of B2 over little b2, which again will be the same as what b1. I really don't need to enumerate the things that are staying the same, but well, it's fine. Okay, so little c2 will be equal to sine of capital C2 times that fraction upside down when I solve for that via some algebra, and then I'll get that. So now I'm plugging in the B2, which is the 114.2, and C2, which is 22.7, and then that the side measure B2 will still be the same that it was right here, 248.6. So C2, I'm going to go ahead and just calculate it. C2 105.2 approximately. Okay, now what I'd like to do, since I got a little messy, I want to draw these two triangles and show you what's going on here. So as I've named them, we have triangle 1, let's see, it's not perfect, but here's A, which was given as 43.1 degrees. B, let's see, for B here, so angle B was 65.8 degrees. That's the first one. That's the angle B that the sine inverse function actually gave us. That's in quadrant 1. Then we found that angle C, just via some geometry here, is 71.1 degrees. And what was given? Side B here was 248.6. Side A is 186.2. And then side C1 was 257.8. Okay, now triangle 2, some stuff is the same. Some stuff is the same. What's the same? The angle A, the side B, and the side A. Okay, so it's more like this sort of. Oof. Okay, with this being A, this being B, and this being C. So let me go ahead and write down angle A was 43.1 degrees. Angle B, so this is like triangle 2, B2 then. B2 we found as 114.2 degrees, and then with that we got the angle of 22.7 degrees for angle C. Side A was held constant, right? That was given, and side, oh no, what have I done? Oh, okay, that's B. Okay, there we go. Sorry, I just misspoke. Side B is the given, side A is over here, given 186.2. And then little side C over here now was calculated, so that we call that little C2 was 105.2. Okay. So again, with this particular case, which is so-called side-side angle, you can have possibly two solutions depending on how the angle, that missing angle is acting. If the given angle is small enough, and then the other angle, both versions of it are small enough to make room for the last final angle, then you have this case where there's two triangles. All right, let's look at the no solution case. So what happens there? This is example 5. Okay, I'm going to solve the triangle. And again, this is a side-side angle. Side-side angle. And let's say that it's like sort of this. It's not a right triangle. I kind of drew it like a right triangle, but it's not. This is 42 degrees. This is 122, and this is 70, and we'll put B down here this time and C up here. Okay. Alrighty, so let me go ahead and label these sides so we don't get mixed up. This is little c, this is little a, and this is little b there. Alright. Let's try to find, what shall we try to find? I don't know. Angle b. Let's try to find angle b. So I'll say sine of b over little b is equal to, definitely want to use a here because I know angle a, so sine of angle a over little a, because I know angle a and little a. Good. And I know little b, right? So I'm going for this b. So solving this all at once, I'll multiply by b over here, so that'll give me that sine of a over a times b, and then I'll also take a sine inverse of that. Good time to just make sure that your arithmetic, or rather algebra skills are good here. Okay, I'll plug this in. I'll go ahead and write in what the values will be. Sine of a, that's going to be 42 degrees over little a is 70, and then times b, which is 122. And let's see what happens with this one. And how will we know that this in fact has no solution? Like, is it going to jump out at us, or is it kind of like, you know, with the back here in example 4, you could have missed this, right? You could have never have known there was a whole nother triangle without remembering that the sine inverse yields 2 solutions, and to check that one that's in the second quadrant. You could have gone a long time with never noticing that, right? Until one of the questions asks for 2 answers, and then you go, what is, there's 2 answers, right? So is there going to be a similar thing happening here where we have to be clever and note that, you know, note something to figure out that in fact no such triangle exists like this? Well, let's see. Let's just start going through the calculations and see what happens. Times 122. Oh, you know what, let me do that the other way. I'm going to do times 122 and then divided by 70, just to make sure my calculator doesn't. Domain error. Okay, so I'm getting a domain error. Why? What does that mean? It means literally I've broken out of the domain of sine inverse. Sine inverse of x has domain, just some if x is just the input, generic input here, has domain of oh goodness, has the domain of what is the range of sine, right? -1 to 1, so that's the domain of the inverse. -1 to 1. Okay, what does that mean? Well, sine of 42, this thing inside, times 122 divided by 70. Sine of 42 degrees times 122 all over 70, which is this, right? I can extend this fraction bar, no problem, is greater than 1. It's outside the domain. You see, that's greater than 1. Thus, no such triangle exists. So, in answer to the question of, do we have to be clever to realize that there is in fact no solution? No, because the sine inverse function told us. We didn't have to do anything. We didn't have to be clever and say, oh, don't forget, you know, about the second solution in the second quadrant like we had to for the 2 solution case. This just plops right out because you try to plug in something that's outside the domain of the sine function. The sine inverse function is saving us here from having to be clever because it just tells us, the calculator just said domain error, there is no solution. Okay. So this is as far as we can get with, or well, this problem is done. There's no solution. But on the whole, to be able to solve the side angle side, which was the example I example 3 that I said we'll stick a pin in. And also to be able to solve the side-side-side case where you're given no angles, we need to now go to section 5.6, which is the law of cosines. And I'm going to go straight there. It's all going to be one video. All right. Think of the law of cosines as the Pythagorean theorem, but for any triangle. It says this: if you've got a triangle with angles A, B, C, as we did before, let's name everything the same, just like we did before, we have this relationship. A squared is equal to B squared plus C squared, and you may say, wait, that's not right because this is not a right triangle necessarily, right? So that's not done though. The rest of the formula is minus 2 times B times C times the cosine of A. This extra term is what's going to beef up this Pythagorean theorem to make it legitimate for any triangle. We have two other iterations of this. B squared is equal to A squared plus C squared minus 2AC cosine of B. So, and there's one more. I'll get them all down and then we'll look at how you can remember these. Minus 2AB cosine of, so this is a product. I'm going to put a dot here so we know that that's a C and then the cosine starts. Right? Capital C. Okay. So I think they're fairly easy to remember because the first part of it's all just Pythagorean theorem, just mixed around, right? For the second part, just remember that it's always minus, it's always 2, and then the side measurements being multiplied are the same as these two, so B and C, and then the angle is going to be the corresponding angle that's across from the side that's isolated over here. So see AC happening, AC, and then B, B, and then AB, AB, and then C, C. Okay. I'll give you these formulas on the exam, the final exam. The law of sines and the law of cosines. This is the law of cosines. All three of these together are called the law of cosines. Okay, so let's go back to example 3 now that we have this tool and see where we can get. So I'll actually rewrite it. I'll just call it example 6. Solve the triangle. Now, these formulas look worse than the law of sines, and they are. They are worse. Worse in the sense that they're more work, right? But you will only need to do them in the cases where the law of sines doesn't work, which is the one we're about to do, and the other case where you have just sides and no angles. And you only have to do it once, because once you find one of those other missing pieces, now then from there you can just use the law of from there you can just use the law of sines. Okay, so where is the triangle? Let's go ahead and get this written down. Just draw it like this. C was 60 degrees, B was unknown, little c is here. Little a was 290 and little b is 340. Okay, I hope this works out right. I made these numbers up. I'm a little nervous. That should be okay. They're not too crazy. Okay. So we already know the law of sines doesn't work, right? We tried law of sines. So let's use the law of cosines to find one of these missing pieces that is being a nuisance, right? If we could find side C, then we would have both angle C and side C, And that would be enough for us to then go to be able to finish the problem with the law of sines. So let's use c squared equals a squared plus b squared minus 2ab cosine of c to find little c. Okay, let me go backwards a little bit here. How did I know, first of all, that I want to find side c? It's always useful to find the side that's opposite to the angle that you know. Because think about the law of sines. If I can find it. The law of sines, each piece of this equation is dependent on the angle and then the side across from it. Angle, side across, angle, side across. If you can get both of these pieces, then that's good, right? That's good. That means you're going to be able to set up the rest of the law of sines and solve the triangle just via the law of sines. So I know that if I'm given angle C here, then I want to go for side C. Now, how did I know I wanted to use, in particular, this equation instead of either of these? Well, because C is already pretty much solved for by itself, nearly by itself, right? It's just like if I chose this one, this top one, I would have to solve for this little c and move a bunch of stuff across the equal sign. Don't do that, right? Just use this. Okay, so I'll say c squared is equal to a squared plus b squared minus 2 times a times b, oof, I'm going to run out of room, cosine of 60 degrees. Which, that's actually a nice angle. Cosine of 60 degrees, but we'll just use the calculator. So first I'm going to figure out what all this is, and then I'll take the square root. So let me go ahead and write down c squared is equal to, so 290, where's my, oh, squared plus 340, excuse me, squared minus 2 times 290 times 340 times cosine of 60 degrees. And I'm getting that crazy number, 101100. And then I'll square root it so that c is equal, and I'll round to a whole number, 318. Good, 318. Okay, now I can use the law of sines to finish this problem, because now I can say sine, what do I want to go for? I'll find angle A. Sine of A over little a, and now since I know angle C and side C, that's what I'm going to use here in my setup. So then I'll go this way just to save some space here. Sine of A, well, A is the unknown thing, right? Over little a, which is 290, is equal to, sine of 60 degrees over 318. So angle A is going to be equal to sine inverse of all of this stuff. So I'll say sine inverse, I'll multiply by 290 times sine of 60 degrees all over 318. (290) times sine of 60 divided by 318. Okay, and I'm getting 52.1 degrees. Again, I'm going to round to the whole number. A is, oh, I should say approximately. I should have said that for little c too. Approximately 52 degrees. Okay. That means that what will be angle B be? Well, B, or angle B, whatever, should be approximately then equal to 180 minus the given angle, 180 degrees minus the angle A, or, whoa, wait, angle C, sorry, angle C, which was given, and then minus angle A, which is equal to minus 60 minus, oh no, what have I done? 180 minus 60 minus 52, which is 68 degrees. So that, that finishes it, right? Because that's all I needed. I got side C via the law of cosines, and then I got angle A via the law of sines, and then I got angle B just via some geometry here. Now, let me back up a little bit and go back to the sine inverse thing, right? Sine inverse outputs two solutions. I only wrote down one of them. Let's see if there is in fact a second triangle. So, or, right, how do I find that angle that's in the second quadrant? I just do 180 minus that given angle, so or 128 degrees. Can already tell that's too big because my other angle is 60 degrees. The given angle, C, is 60 degrees. That's going to be too big, right? Because 60 plus 128, that's above 180. But if you don't believe me, let's check. Let me show you maybe a little bit more explicitly. So my triangle would be, so if A is approximately 128 degrees and C is equal to 60 degrees, then B is equal to 180 minus that 60 minus that 128 degrees, which would be I guess I should say approximately, since I've been rounding, and that's fine to say equals here, but okay, so 180 minus 60 minus 128 is -8. Does not, so this is not possible. So we do not need to consider we do not need to consider the other angle. In fact, you only need to consider it when you're dealing with the side-side angle case. So when you've got this case, when your angle is sandwiched between your two sides, you don't need to worry about the sine inverse thing giving you two solutions and possibly two triangles. Okay, so this is like the worst the process can get. There's strictly using law of sines, the math is not too bad. It does get a little weird when you get that case where there's two possible solutions. And then the other kind of bad case, I guess, is when you are forced to use the law of cosines because the law of sines is not enough. But you see, you only have to use the law of cosines once, and then you will have enough from there to use the law of sines for the rest of the problem. Let's do the last case where, what am I on, example 7, where you're just given sides, strictly all sides. Again, all the instructions here are just solve the triangle. There are some neat little application problems that the book goes over, but you know, yeah, I think we'll just stick to the basics though. Okay. So this is going to be a side, so-called case. Let's make this A, B, well, A, C, and B. Oof, didn't mean to miss that line there. There's A, B, and C. Little c here is 12, little b is 8, and little a is 5. Alright. No luck with the law of sines right off the bat. I know that because I don't have any of the angles. All of the law of sines formulas depend on it in angle, right? No matter what I'm doing here, there's always two angles, and I can't have two unknowns, right? I can't have two unknowns, so I've got to get an angle. So I'm going to have to use the law of cosines. And which one do I use? Which one do I use? Which one of these law of cosines do I use? Well, it really doesn't matter. So what I'm going to be solving for is one of these angles, and it honestly it doesn't matter because you just need one of them. So I'll just go with the first equation there, and the algebra is going to be a little gross because I have to solve for this angle, but I'm going to do it generically without plugging anything in, just so you can see how that goes. Okay, so I'm going to use this formula, a squared equals b squared plus c squared minus 2bc times cosine of a. And I want to solve for that capital A, which is buried in a cosine function. So I know at the very end I will be taking a cosine inverse. Okay. First I'll go ahead and scoot these two things over, so I'll have a squared minus b squared minus c squared, and then negative 2bc times cosine of a. Okay. And then I'm going to divide by this whole thing, negative 2bc. So I'll have a squared minus b squared minus c squared all over negative 2bc is equal to cosine of a. And then I'm going to scoot this over just for the sake of space. I'm going to do something here before I take the cosine inverse, just to clean this up a little bit. I'm going to use up this negative that's in the bottom and make it flip all of these signs so that I don't have this negative going on in the bottom. So I'm going to have negative of a squared plus b squared plus c squared all over 2bc. So think of it, maybe an easier way is back here. Think of it as me dividing by just negative 1, which effectively would get rid of this negative on the 2bc and also flip all of these signs. Okay. Oh, I need the rest of the equation, right? Cosine of a. Okay, now I'll take a cosine inverse on both sides, which I know will cancel this cosine because they're inverse functions, and it'll just plop out the input, which is a, which is what I want. So I'm going to need the cosine inverse of this whole thing. So I'll write it. I'm writing it backwards. There we go, and cosine inverse of this whole thing. So there is my angle A. So now I will come up here to do the, well, goodness, yeah, I guess I'll use this space over here. A is going to be equal to cosine inverse of negative, and A is 5. And remember, the negative's on the outside of the square, so it will be negative 25. And then plus, now I don't need parentheses here. There's no minus signs. I'm not worried about dropping a negative or anything. It's all positive for these two. And then 2 times 8 times 12. There we go. That's it. So plugging this all in at once. Cosine inverse. Now for my calculator, I don't have that little like fraction button that maybe some of y'all might have. So I have to do this like the old-fashioned way. So I'm going to say negative, then parentheses 5, and then, well, actually I can just use the squared button, and then plus 8 squared plus 12 squared. Now when I divide here, I'm going to need to wrap the denominator in parentheses so that it knows I want to multiply all these together in the denominator. Okay, you don't have to worry about that if you've got one of those calculators with the little rectangle over rectangle, the little fraction button that lets you actually input the fraction pieces. And now I need to close the parentheses for my cosine inverse. Oh no, that should not be what I get. What happened? Okay, that shouldn't happen. I plugged something in wrong. Let's see if I can go back through. I don't know. I guess I'll just try it again. Cosine inverse. You know, since the calculator's giving me issues, I'm going to figure out what this is and then plug it into the cosine inverse. So I'll say negative 5 squared plus 8 squared plus 12 squared divided by 2 times 8 times 12. Okay. Oh, I did such a dumb thing. I need to wrap my numerator in parentheses too, otherwise the calculator just thinks I'm trying to divide 12 squared by all of this stuff instead of the whole thing. That's a rookie mistake. Okay, so another set of parentheses, then negative 5 squared plus 8 squared plus 12 squared. Close my numerator, start my denominator in parentheses 2 times 8 times 12. Close that denominator, close the cosine inverse. There we go. It's much easier if you have one of those calculators that just has that fraction button. A is approximately, let's see, what are we rounding to? I'm going to say like 18 degrees. Yeah, 18 degrees. Okay, now what the book does at this point is they keep going and they do this for all three angles. They use the law of cosine for all three angles. But you don't have to, because as soon as you get one of these missing pieces, now you can use the law of sines. So I'm going to cover all this algebra up, and I'm going to say now that I have the angle A, I'm going to get this sine of A over little a involved, because I know both of those pieces, and now I can find whatever I want, these other two missing angles, I can find via the law of sines. Yes, law of sines. So dot 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 B is going to be equal to, I've already done the algebra so many times, let me just go ahead and just tell you, you know, you're going to plug in A is 18, you're going to plug in little a is 5, little b is 8, solve for sine of b, then take the sine inverse, and you're going to get 29 degrees for b. And then you'll do a similar thing, sine of capital A over little a. So you see, as soon as you find one of the missing pieces, just go right back to the law of sines. The law of sines is much easier algebraically than the law of cosines. So angle C is going to be 133 degrees. And there we go. That's all of the missing pieces here. By the way, back here, I got an answer from an inverse trig function, or trig operation, I should say. Do I need to think about, like the sine inverse one, how it gives me two answers, right? So sometimes that was an issue with the sine inverse operation. What about here? Not an issue here, because cosine inverse does give you two solutions, but where are they? They're not in quadrant 1 and 2 like sine. They're in quadrants 1 and 4. That's where cosine is outputting its two positive solutions, right? And this, or, well, rather, what I mean for that is that's where it outputs if you give it a positive input, is what I meant to say. It outputs in quadrants 1 and 4. And this angle down here is much too big, right? This is the 18-degree angle, and the other one, even if you consider it as a, well, first of all, you can't consider it as a negative angle. That makes no sense in the context of triangles. So if you go around positive, it's way too big, right? It's way too big to be an angle inside of a triangle. So no need to worry about that issue when you're dealing with the law of cosines when you take that cosine inverse. All right, that is it for law of sines and law of cosines. I am not particularly worried about you knowing the sort of crazy cases where you can have 1, 2, or 0 solutions. I'd just like for you to be able to do a problem, just kind of a simple, straightforward law of sines problem with just one solution, and then also a problem either like example 6 or 7 where you're forced to use the law of cosines once and then finish the problem with the law of sines. Okay, that's it.